Hello friends, welcome to Semi World once again. Let's start our second training video of Verilog. In last training video, we had covered hierarchical modeling and basic concept of Verilog. In this video, we will cover module ports and their connections. In the later videos, we will cover gate level modeling, data flow modeling, behavioral modeling, tasks and function, and some useful modeling techniques. In modules and ports, we will cover Verilog module definition and its components, definition of the port list for a module and declaring it in Verilog, port connection rules in a module instantiation, connecting ports to external signals by ordered list and by their name. Let's see the component of Verilog module. Module definition starts with the keyword module and module name, the input, output and in-out port declaration. Then parameter declaration, which is optional. Then declaration of internal wires, registers and other variables. Data flow statements like assign as per requirement. Always and initial blocks. All behavioral statements come in these blocks. We will learn about always and initial blocks in behavioral modeling topic. Instantiation of lower level modules, tasks and functions, and in the last end module statements. So these are the components of Verilog module. Let's see one example of D flip-flop to understand the components of module in earlier slide. So before we start with the example, this time we will simulate our design in simulator and will debug the design. We will use EDA playground to practice the example. It's free EDA tool which is very helpful for the students who want to practice coding and simulating their design. First, I will explain the full design and test bench code in PowerPoint slides, and then we will write the same code in our simulator and simulate them. Module definition starts with the keyword module and module name D flip-flop. Then in the small brackets, these are the port list: D in, clock, reset, and D out. Then these are the port declaration. Port declaration define the direction of the ports, whether it's input, output or in-out port. And this is always block is behavioral block, which represents the functionality of the D flip-flop. This always block will execute at every passage of the clock. So once it sees the positive edge of the clock, it will enter the always clock and check if there is a reset active or not. If reset is active, then D out would be 0. Else if reset is not active, then D out will be equal to D in. So as you can see, it's exactly represent the functionality of the D flip-flop. At the end module statement will be returned. Okay. So here we have designed the D flip-flop by using Verilog code. Now to verify our D flip-flop design, let's see how can we write testbench module for that. Verification module also starts with the keyword module and module name tbtop. Here TB stands for the test bench. Here we haven't mentioned port list for the tbtop because it's not connected to any other higher level module, and that's why we have given the name as a tbtop, means top level module. Then we are declaring internal variables of the tbtop: tbdout, tbdin, tbclock and tbreset. Now we will instantiate D flip-flop design module with the tbtop module. It means we are making connection with D flip-flop input output ports and internal variables of the tbtop. Here you can see that we have mentioned all internal variables in the ordered list with respect to the D flip-flop port list. TBD in with the D in, TB clock with the clock, TB reset with the reset, TBD out with the D out. Now for clock generation, we have this behavior always block, which is always execute, and at every 5 time units delay, it will toggle the clock. Then this is initial behavioral block to provide the stimulus to our design D flip-flop. In this block, we are assigning value 0 to the clock and reset is active high. So initially D flip-flop is in reset. Then after 5 time units, we are making reset low, which means D flip-flop is out of reset. Then we are providing input D in as a value 1, which should give output D out is equal to 1 after 1 clock cycle. Then we are providing D in as a 0, so we should get the D out as a 0 after 1 clock cycle. And at the end, we will write AND module. So our test bench is ready. Now let's write this code in EDA Playgrounds simulator. So let's simulate our D flip-flop design in our EDA Playground tool. So for that, open any search browser. I'm opening the Google Chrome. So here in search engine, you can just search for the EDA Playground. Okay, and you will get this page www.edaplayground.com. Just click on it. So you will get this page. So first you need to create your account here. I have already created it. So once you create the account, then only you will be able to run your code. You can see here we have a design.sv file and testbench.sv file is there. So in design.sv file we will write our D flip-flop code. You can see here comment code your design here. So we will design here our code, and in testbench we will write our TB top module, which I explained in earlier slide. Okay. So once you create the profile, we can start with it. So here I have already created profile, so I can go to my profile and I have already written that code, so it will save over time. Okay, so yeah, so you can see here this is our D flip-flop design, which I explained you in earlier slide, and this is our TB top module, and this is instantiation of D flip-flop, which I showed you in our earlier slide. So only difference is in that code is like I have added two lines here, dollar dump file and dollar dump parse. These two lines is for to generate the waves. Okay, so we will be able to see the waveform of D flip flop, and this dollar monitor display I have written it to just in log file. We will be able to see the values of clock, reset, D in and D out at every time units. Okay, this is our stimulus, and I have added here dollar finish to terminate the simulation. So once you write your design here and the test bench, you can from tool and simulators you can select your tool. You need to select it. So I have selected LDEC Rivera. I will show you what else tools are there. So we have LDEC Rivera simulation simulators, Cadence simulator, Mentors simulator, Synopsys simulator is also there. Okay, so you can select any of. I have selected LDEC Rivera. Once you select it, you will get the compile option here. Time scale 1 nanosecond by 1 nanosecond. This I will explain later. And run options also, it is automatically it will come. And here in your page, this option will not be selected. So you need to explicitly select it to check to open the waves. So here if you see, this is EP waves. After run, once we run this, it will open the EP waves, and we will be able to see the our design in waveform. Okay. So our code is ready. Okay, just we need to run it. So you will see the log here once I run it. So let's start it. Okay, it started. Okay, so this ep wave window popped up. So this is waveform which we will see later. First we will see the log file. So our run is ready. So you can see here, you can see the messages like pass one scanning module hierarchies, then processing instantiation which we have done here, and processing behavioral statements which we have written in always an initial block. Okay, then you can see that our compilation is success, zero errors, zero warning. Okay, then we will see elaboration phase, that is also finished. Okay, then this is simulations. So you can see here as per our print uh, in dollar monitor, you can see we are seeing the prints in log file. Let's just drag it down a little bit so we can see it. Okay, so this, you can see we have printed clock, dollar time, which is given here, and comma dollar clock, reset, d in and d out. So whenever this signal changes, tb clock, tb reset, this print will come. So here we are changing the clock at every 5 time minutes. As you can see in this always block tb clock, we are just toggling every 5 time. Okay, so 0, 5, 10, 15, we can see the values, and at 0 time we are assigning 0 clock value 0, reset value 1. So our d flip-flop is in reset initially, and tbd in as a 0. So you can see this value here. D out is x, so it's default value of the register. We are not assigning any value to the d out because it will be assigned by the d from the design, as you can see here. And after 10 time units we are making tb reset 0. So here at 10 time unit you can see that reset value has changed from 1 to 0. So our d flip-flop is out of reset. D in is same as 0. We haven't given assign any value to d in at 10 time units, and d out also will be 0. At 15 time units, tbd in we are assigning 1. So 10 plus 15 is 25. So we need to see at 25 d in is assigned 1. Okay, so we can see the value 1 has been assigned here, and for one clock cycle it will be 1 only, and after 10 time units tbd in will be 0. So you can see at 35 tbd in is 0, but we can see the output here, d out is equal to 1. So that is exactly after one clock cycle, which we will see in the waves also. Okay, this is from this log we can see that as per d flip-flop functionality we are getting the output after one clock cycle. So there is a difference between d in and d out, one clock difference between input and output. That's what exactly the d flip-flop functionality is. Okay, then you can go a little down. So at 50 time units, dollar finish is called. You can see in the log file. So we have invoked dollar finish here. So it will terminate the simulation. So our simulation has finished at this time. Okay, you can see this message that simulation has finished. Okay, so that's how we can refer the log file also. Okay, and now let's see the waves. Okay, so in the waves, you can see the TB clock is toggling after every 5 time minutes. See, 0 to 1 it is going. This is 5 time minutes. At 10 time minutes, the whole clock is 0 to 1. Then again at 15 it is going high, 20 it is going low. So like that it is. And then TBD in initially it is 0. TBD out is also 0. From X to 0 it is going, and then TB reset we can see at 10 time units we made it 1 to 0. So we can see that in the waves. So here D flip-flop is out of reset, and then at time 35 we are sorry, at time 25 we are assigning TBD in one value. So for one clock cycle we can see that this value is a high, and after one clock cycle we are getting the output TB T out. So which is exactly the D flip flop functionality. Okay, so that's how we can verify through waves as well as through logs, and we can also write checks in the test bench to make sure that the D out comes exactly after one clock cycle. So that checks we can write here in initial begin, but that part is verification part, which we will not cover right now. We will cover it in system Verilog sessions. So right now we are focusing on the design side. So we have designed it, and this is very simple stimulus to check this design whether it is working fine or not. So you can write any design, small design here. You can code it, and here you can write the test bench and write a small stimulus like an initial begin. Okay, and give a monitor and run it here. So this button, and you can check whether your design is working as per your specification. Okay, so that's how we practice designing in EDA playground. Okay, ANSYS style port declaration. Here we declare the port's direction in port list itself. So here you can see with DN we have decided direction as an input. Clock direction is also input. Reset direction is also input. And Dout's direction is output. So that will reduce the number of lines in our code. It is called ANSYS style port declaration. We recommend to use this ANSYS style port declaration in Verilog. Now, now let's see port connection rules. Module's input wire can be connected to external modules wire or ridge. Module's output ridge or wire must be connected to external modules wire only. Module's in-out wire must be connected to external modules wire only. So these are the port connection rules of module. Now connecting modules by ordered list and by their name. We have seen module connection by ordered list in earlier slide. Let's see that again. Here we have a module of D flip-flop design. It has a port D in, clock, reset and D out. Then we have external module TB top. In TB top module, we will connect our D flip-flop design by instantiating it like this. Here if you see, TB top variables are declared in ordered list with respect to the D flip-flop design. TB in with D in, TB clock with clock, TB reset with reset, TB D out with D out. Now let's see port connection by their name. Here .D in is D flip-flop signal, and in the bracket TB top D in signal. Same way dot clock is D flip-flop signal, and in the bracket TB top's clock signal. Reset with TB reset and D out with TB D out. So that's how we can connect the port by their name. When we connect the port by their name, we don't have to worry about their order. Let's see one more example of D flip-flop instantiation. Here we have first connected the clock and then D in, then D out and reset. So as you can see, these ports are not in order with respect to the D flip-flop ports. So we recommend to instantiate the module name by port's name. This is end of the session here. Till now we have covered hierarchical modeling and Verilog's basic concept. In current session we have covered modules and ports. In next session we will cover gate level modeling. In later sessions we will cover data flow and behavioral modeling, tasks and function and useful modeling techniques. Thank you.